According to the National Electrical Code, the minimum size conduit for a 2,500-foot underground electric service depends on the amperage of the service. For services rated at 200 amps or less, the minimum conduit size required by the NEC is 3 inches. If the service is rated between 201 amps and 400 amps, the minimum conduit size increases to 3.5 inches. Therefore, a 2-inch conduit is not permissible for an underground electric service of this length. This is because the National Electric Code specifies standards for safety and proper installation. These standards ensure that electrical systems operate safely and efficiently. Choosing the right size conduit is part of these standards. Smaller than recommended conduits can lead to overheating and potential damage to conductors, and also make pulling conductors very hard, damaging the insulation in the process. Larger than needed conduits waste budget. The NEC dictates the smallest acceptable size, so it is important to follow those guidelines. Conduit size is not the only factor to consider. The type of conduit also matters. Options include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, rigid polyvinyl chloride conduit, and high-density polyethylene conduit. Each has specific applications and limitations. Rigid metal conduit, or RMC, is typically made of steel or aluminum. It offers the highest level of protection against physical damage. It is often used in exposed locations or areas where severe physical damage is likely. Intermediate metal conduit, or IMC, is a thinner-walled version of rigid metal conduit. It provides good protection but is lighter and easier to work with than RMC. Electrical metallic tubing, or IMT, is a thin-walled conduit commonly known as thin-wall conduit. It is suitable for indoor use and concealed locations where it will not be subject to severe physical damage. Rigid polyvinyl chloride conduit, or PVC, is a non-metallic conduit that is resistant to corrosion. It is often used in underground applications or in areas with corrosive atmospheres. High-density polyethylene conduit, or HDPE, is another type of non-metallic conduit. It is flexible and resistant to chemicals, making it suitable for direct burial applications. When installing underground electrical services, the depth of burial is also important. The NEC specifies minimum burial depths for different types of wiring methods and voltage levels. These depths are designed to protect the wiring from physical damage and ensure that it remains safe. For example, direct burial cables typically require a greater burial depth than conduit encased cables. Backfilling around the conduit is also important. The backfill material should be free of sharp objects that could damage the conduit. It should also be compacted properly to provide support and prevent settling. The type of conductor used within the conduit is another consideration. Conductors must be sized appropriately for the load they will carry. The NEC provides tables that specify the allowable ampacities of different types of conductors based on their size and insulation type. When selecting conductors, it is important to consider the ambient temperature and the number of conductors in the conduit. High ambient temperatures can reduce the ampacity of conductors, so it may be necessary to use larger conductors or derate the existing ones. Similarly, when multiple conductors are installed in the same conduit, their ampacity must be derated to account for the increased heat buildup. Proper grounding is essential for electrical safety. The grounding system provides a path for fault current to return to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. The NEC specifies requirements for grounding electrodes, grounding conductors, and bonding. Grounding electrodes must be installed in contact with the earth and must have a low resistance to ground. Grounding conductors must be sized appropriately for the size of the service and must be connected to all metal enclosures and equipment. Bonding is the process of connecting metal parts together to create a lower impedance path for fault current. This helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect wiring and equipment from overloads and short circuits. These devices must be sized appropriately for the load they will carry and must be installed in readily accessible locations. The NEC specifies requirements for overcurrent protection, including the types of devices that are permitted, their ratings, and their installation requirements. Surge protection is also important, especially in areas that are prone to lightning strikes or power surges. Surge protective devices, or SPDs, are designed to protect sensitive electronic equipment from voltage spikes. These devices divert surge current to ground, which helps to prevent damage to equipment. SPD should be installed at the service entrance and at any other locations where sensitive equipment is located. Electrical inspections are an important part of ensuring electrical safety. Electrical inspectors review electrical installations to ensure that they comply with the NEC and other applicable codes. They also verify that the installation is safe and that it meets the requirements of the local utility company. Electrical inspections are typically required for new construction, renovations, and additions. Permits are often required before electrical work can begin. Permits help to ensure that the work is performed by qualified individuals and that it complies with all applicable codes. The permit process typically involves submitting plans and specifications to the local building department and paying a fee. Once the work is complete, an inspection is required to verify that it has been performed properly. Working with a qualified electrician is essential for ensuring electrical safety. Electricians have the training and experience necessary to perform electrical work safely and in compliance with all applicable codes. They can also help to identify potential hazards and recommend solutions. When selecting an electrician, it is important to check their credentials and ensure that they are licensed and insured. It's important to understand the voltage drop across the 2500-foot run. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and can also damage wiring. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of the conductor depends on its size and material. Larger conductors have lower resistance than smaller conductors. Copper conductors have lower resistance than aluminum conductors. The NEC provides tables that list the resistance of different types of conductors. Once you have calculated the voltage drop, you can compare it to the recommended limits. If the voltage drop exceeds the limits, you will need to use larger conductors or reduce the load in the circuit. Another consideration is the presence of any underground utilities in the area. Before digging, it is important to contact the local utility companies to locate any underground utilities. This will help to prevent damage to the utilities and ensure the safety of workers. Utility companies typically mark the location of their utilities with colored flags or paint. It is important to dig carefully around these markings to avoid damaging the utilities. If you damage an underground utility, you should immediately notify the utility company. They will dispatch a crew to repair the damage. The type of soil in the area can also affect the installation of underground electrical services. Some soils are more corrosive than others, which can damage conduit and conductors. In corrosive soils, it may be necessary to use corrosion-resistant conduit and conductors. The NEC provides guidelines for selecting corrosion-resistant materials. The presence of groundwater can also affect the installation of underground electrical services. Groundwater can cause conduit to corrode and can also damage conductors. In areas with high groundwater levels, it may be necessary to use waterproof conduit and conductors. The NEC provides guidelines for installing electrical services in wet locations. When installing underground electrical services, it is important to follow all safety precautions. Wear appropriate personal protective equipment, such as gloves, safety glasses, and steel-toed boots. Use caution when digging and avoid contacting any underground utilities. Never work on electrical equipment while it is energized. Always disconnect the power before working on electrical equipment. If you are not comfortable performing electrical work, hire a qualified electrician. The NEC is updated every 3 years, so it is important to stay up to date with the latest requirements. The NEC is published by the National Fire Protection Association, or NFPA. The NFPA also offers training and certification programs for electricians and other electrical professionals. Understanding the National Electrical Code, or NEC, is essential for ensuring the safety and proper installation of electrical systems. It is a comprehensive set of standards that covers all aspects of electrical work, from wiring methods to grounding to overcurrent protection. The NEC is adopted by most states and local jurisdictions in the United States. It is also used as a reference standard in many other countries. The NEC is not a law itself, but it is often incorporated into law by reference. This means that compliance with the NEC is legally required in many areas. The NEC is developed by a committee of experts from various fields, including electrical engineering, electrical contracting, and fire safety. The committee meets regularly to review and update the NEC. The NEC is based on sound engineering principles and is designed to protect people and property from electrical hazards. The NEC is divided into chapters, each of which covers a specific topic. Chapter 1 covers general requirements such as definitions, wiring methods, and grounding. Chapter 2 covers wiring and protection. Chapter 3 covers wiring methods and materials. Chapter 4 covers equipment for general use. Chapter 5 covers special occupancies. Chapter 6 covers special equipment. Chapter 7 covers special conditions. Chapter 8 covers communications systems. Chapter 9 contains tables and examples. The NEC contains many tables that are used to determine the proper size of conductors, conduits, and overcurrent protective devices. These tables are based on the type of conductor, the ambient temperature, and the number of conductors in the conduit. The NEC also contains many examples that illustrate how to apply the code requirements. These examples can be helpful for understanding the code and ensuring that it is applied correctly. The NEC is a complex document, but it is essential for anyone who works with electrical systems. By understanding the NEC and following its requirements, you can help to ensure the safety and proper installation of electrical systems. In the specific scenario, the question describes a 2,500-foot underground electric service for a private residence or vacation home. The response clarified that according to the NEC, a 2-inch conduit is not sufficient for this service. The NEC specifies a minimum of 3 inches for services up to 200 amps and 3.5 inches for services between 201 and 400 amps. There are several reasons for these requirements. Firstly, the conduit must provide adequate space for the conductors to be installed without damage. The NEC specifies the maximum number of conductors that can be installed in a conduit of a given size. Secondly, the conduit must provide adequate heat dissipation for the conductors. When conductors carry current, they generate heat. If the heat is not dissipated properly, the conductors can overheat and damage their insulation. The NEC specifies the maximum allowable ampacity of conductors based on their size, insulation type, and the ambient temperature. Thirdly, the conduit must provide physical protection for the conductors. Underground conduits are subject to physical damage from rocks, roots, and other objects. The NEC specifies the minimum wall thickness for different types of conduit. The local utility company, Conduit, has different requirements for the portion of the service that they install, which is from the transformer pole to the meter base. They require a 3-inch conduit for their portion of the service, regardless of the amperage. However, Conduit has stated that they do not care what size conduit is installed from the meter base to the residence, as long as it meets NEC codes. The NEC is the governing standard for the portion of the service that is privately owned, that is, the portion from the meter base to the residence. Therefore, the conduit size for this portion of the service must comply with the NEC requirements. A 2-inch conduit is not sufficient for this application as it does not meet the minimum size requirement specified by the NEC. To reiterate, the response clarified that for a 2,500-foot underground electrical service, a 2-inch conduit would not be up to code based on the NEC.